indoor-outdoor HDR photography and scene relighting, which is done by me, Azadeh Sawyer, and Srinivasa Narasimhan at Carnegie Mellon University. So we focus on residential light. If you want to buy a house, it's common we need to search online. And for example, if we open the Zillow website, there are millions of homes. And the point is that they are all different from different geographic location and in different conditions and different styles for sure. So the point is how to virtually stage indoor spaces. Yeah, we can see from the website those fancy and carefully polished images. But some people, they visited the website and then traveled to the home and they were like, that's not what I saw from online. And in this case, we hope to achieve realistic lighting from both indoor and outdoor spaces. In the meantime, we need an automatic process to achieve this. So our work is about virtual home staging. In this work, we will collect paired indoor and outdoor images as input with photometric calibration. Then I build an end-to-end inverse rendering pipeline. At the end, it will output virtual rendered scene. So we focus on indoor panorama, and this is just a quick review about what we are doing. For example, the existing house has a lot of furniture objects. So this is an indoor panorama. For the existing room, we automatically convert it into a new furnished room. Here we can see some new furniture objects here, and the new objects are rendered with global illumination. And unfortunately, when I visited this house, it's cloudy. We also estimate the direct sunlight from outdoor space, so we can see how it looks like during clear sky condition. And then we have sunlight now, but even if in the daytime, we still need electrical light. So I add a small standard light here with a warm light. As we can see here, after we add a standard light, two different light sources illuminate the space together. So for this talk, first we will walk through the indoor and outdoor HDR photography. So for indoor scene, I use a Ricoh Theta Z1 camera plus luminance meter. So I set up the camera with a tripod, color checker, and a whiteboard, and then capture 360-degree panorama. For outdoor, I use a Canon 6D DSLR camera plus a fisheye lens. Then the camera is placed outside the room, and we can capture 180-degree fisheye. And then I will use indoor measurement to calibrate outdoor HDR. How to do this? So in this room, under electrical lighting condition, I set up two different cameras facing the same target and use exactly the same camera settings as the data collection. Then we capture the same target from two different cameras in HDR format. And then for those two images, I first crop the target region and then find the raw luminance values from the little white patch and compute the ratio difference between those two areas. And then we can see the image captured by the fisheye lens is rescaled to match the panoramic image. And we have a standard formula to compute the luminance. And I add one more component here. K1 is from the luminance measurement from indoor scene. K2 is a constant. But we have to note here, the camera settings must stay the same. Otherwise, this formula won't stand. And RGB are 3 color channels. So for post-processing steps, indoor panorama, we use per pixel calibration. And then for outdoor images, we need a vignetting correction and equidistant correction, plus color correction and also photometric calibration, as I mentioned earlier. all the photos are captured with daylight 6500. Using this approach, I went to different homes during the daytime and capture paired indoor and outdoor images and repeat this process. So overall, I captured 137 scenes within 10 months and all the data from Pittsburgh region. All right, now I have presented this method. I went to data collection on my own, and I know clearly how much effort it takes for me to capture the data because there are so many components. Additionally, if I list the price here, maybe we should simplify this. So I started to rethink how could we optimize the data collection pipeline. So we propose another low-cost approach. We use one single camera, capture both indoor and outdoor image, and then use a much cheaper light meter to do photometric calibration. Now the price is much lower. So to capture indoor and outdoor images, now I can just control the camera from a smartphone, use a multi-bracket exposure function in Ricoh Theta Z1 camera. And then both indoor and outdoor panoramas, they are captured from the same camera settings. So when I capture outdoor images, there are a lot of different scenarios. First, the most decent scenario is we can open the window and we can place the camera facing the outdoor. However, the window is not always operable. For non-operable window, I need to go downstairs and capture the outdoor images. Okay. Yep. Okay. And then for high-rise building, it's common we cannot open the window. So the solution is that we place the camera as close to the window as possible, and then we can capture the outdoor spatially varying light. And also, if there's a balcony, that's great. So for those cases, we can almost deal with all the outdoor photography scenarios. Next, using this approach, another approach, I captured 141 paired indoor-outdoor panoramas with photometric calibration, and we can see this time is shorter because the data collection is way easier. And I call this panel-to-panel HDR dataset. Okay, for the low-cost approach, how could we do photometric calibration? We have a light meter. And then if we look at the Theta Z1 camera, the single panorama is stitched from dual fisheye lens. Unfortunately, the lens is not a pure 180-degree hemispherical. So what I did is that I focus on the front lens and convert that into orthographic fisheye image. Then we can compare the illuminance value from the light meter and compute the uniform luminance for photometric calibration. Now the point is that how accurate this method is. During data collection, I actually implemented two different methods. First one is standard luminance meter. I measure the target luminance on the whiteboard for all the scenes, 141 scenes. And then use low-cost photometric calibration. After calibration, then select the luminance from the calibrated HDR to compare it with the ground truth luminance value. So and then I can overlap the data together. Overall, for those 141 images, the average absolute luminance error is 3.900. No, 88, sorry. And considering the real world luminance value, we believe this error is decent. So the second part is inverse rendering for scene relighting. Similar to rendering and lighting simulation, standard workflow typically begins from an existing floor plan. Then we have multiple commercial software platforms. Then we do detailed modeling. Normally, it takes several days for architects or professionals, and because they need to have some manual modeling and manual inputs. And then we can select materials, which only takes several minutes, but we can only select approximated materials. And the last, if we know the GPS location, we want to customize the sky condition with customized image resolution, we can provide a standard sky model. It takes several minutes, and we can only select approximated sky model. This is a standard workflow if it's fully virtual. We can use field measurement to improve the realism. For example, we can go to the house, go there in person and scan the room. Then we can get the floor plan automatically. However, it still takes several hours. And then we can bring DSLR camera to capture the real world texture rendering instead of select the material from the library. And at the end, we can use HDR photography and spend a few hours from data collection to post-processing, then do rendering. Overall, this process is not sequential. We need to go back and forth. It's time-consuming and also needs manual modeling. Maybe it's not that efficient if we want to deal with millions of homes. So now we started to think what a single image can tell us. And we have an indoor RGB panorama. And it's a very common research questions in computer vision. There are a lot of deep learning approach. For example, if we use deep learning approach, we send the panorama into the model, then it can give us 360-degree layout. And this process only takes several seconds. Meanwhile, deep learning approach can also help us to classify indoor elements, which also takes several seconds. So as you can see here, different indoor elements are classified into different pixel values. Like a window is white here, and the floor and the wall, and we can see the cabinet. They are all different colors. So for now, using one single image, after we send it to deep learning model, we can get a lot of information. We still have one more image, which is outdoor panorama. Then we can estimate the indoor spatially varying light and get this shading layer. And further, if we implement intrinsic decomposition, we can get a reflectance layer from the captured image. We almost have everything we need to render a space. So our inverse rendering pipeline specifically use paired indoor-outdoor images. Then we will estimating 3D floor layout, reflectance property, spatially varying light. Then because we need to do a design, so we added new floor layout, new materials, new light, and then output the new panorama. Normally, the second column takes most of the time and effort. And we need a manual inputs for the second column and then get the third image. But this time we do inverse the way. That's why we call it's inverse rendering. We only have the input images and get all of the information from the images. Okay, error analysis. This is a plot of the real world luminance value. We tentatively select 2500 candela per meter square as the threshold to analyze the error. First, we have captured the indoor panoramas as ground truth. And then this is a rendered image. I render it in HDR format. Then compute the error map and see the error of the luminous values. So we can see for the indoor surfaces, it's fine, and the error is low. And most of the error comes from the window. But considering the high luminance in the outdoor space, I think the error is decent as well. So the last part is applications for scene editing. So this is an indoor panorama. For most of the cases, when we visit the house, it's furnished. And removing the furniture objects is a big pain. So first, I propose an approach to automatically remove the furniture objects. Here we can see all furniture objects are gone. But we still can see some leftover like shadow here. And then the process is we need to automatically detect furniture in a panorama. So for this top left corner image, human eye can somehow find the furniture objects, although we can see the distortion due to the equirectangular representation. So what we did is that we crop it into multiple 2D perspectives and label field of view, theta and phi angles. Then run semantic segmentation, as I mentioned earlier, we can classify indoor elements into different pixels. And then we only filter the furniture objects. Since I have the annotation for each image, we can stitch all the furniture mask back and filter the pixel for furniture objects. Then this mask will be used to guide furniture in painting process and get empty room. So we have a clean room, then I have my own preferred furniture objects. So I hope to have a test to see how my furniture looks like in this room. So for furniture layout, first we have two inputs, furniture object and the floor mesh. The parameter inputs are orientation and location. We send the two models into 3D coordinate. And then we can choose either it's facing the window or side to window. And then the parameters are distance to window and distance to wall. At the end, it outputs adjusted furniture objects. It's just a visualization. I know Rhino can do the same thing, but all the process here happened in a black box. We cannot see that. We only have input and output. So for virtual staging, each object has its own textures and materials. We can render everything with global illumination now. We can see some slightly shadow under the desk. And then next, although I only capture one single image, as a buyer, I may not like the texture. For example, here I change the floor texture. And also I change the wall on the right. And we just have one single panorama, but it's possible to move into a new indoor location to see how it looks like. Yes, so here is another example. If we capture an empty room, the single panorama can be furnished with a new object. For empty room, we don't need to remove the furniture object. And then we can change indoor position in 2D perspectives. For example, the 2D perspective in position 1. And the 2D perspective, if we move closer to the couch. And the last one, if we move closer to the bed. Okay, because we also capture the outdoor images, it's not just providing outdoor real-time spatially varying light. It can also help us to visualize what's going on outdoor. For example, the left image, the indoor looks decent, but if you look at the outdoor, it's a gas station, maybe it will change your decision if you want to buy this house. For the second room, you can see outdoor, it's near a street, but it has a very open view to outdoor. So it will also impact your decision. Okay, now I have presented how to edit indoor images. We also edited outdoor images. So we captured the outdoor 180-degree fisheye. And to find where the sun is using camera orientation, we can somehow locate where the sun is. First, we convert a 180-degree fisheye into equirectangular representation. Then this image can be used as an environment map for rendering. And then for image, the map data can tell us the GPS location and the time. In that case, we can find the theta and phi angle for the sun. Here, I annotate the sun, where the time, when I capture the data. And we can also estimate where the sun is. For example, I select a random time. I want to see where the sun is. So here's an example. When I edit outdoor images, we use one single image as input, then estimate where the sun is in the future during the same day. During this process, we also render the full spectral sky model, so we can see slightly color change during the day. And there are three different things. And okay, so here the left column shows using paired indoor-outdoor image for virtual home staging, and the right image we rendered the image use edited outdoor images. We can see the sun changes. So using this approach, we don't need to visit the house multiple times. In the meantime, if we look at this scenario, the outdoor has a clear sun, and since we know where the sun is, we can create a virtual sun mask and remove the sun from the outdoor image. Then we can render exactly the same room, same time, but without direct sun illumination. So another example is that for this house, when I visit the house, it's cloudy outdoor. And since we know where the sun should be, and we know the absolute sun brightness in luminance, we can create a virtual sun mask and render this room under clear sky condition. Yeah, all the effort here is that we assume we can only visit the house once, then estimate different outdoor sky conditions and render the room at a time series. So not just for daytime, we also care about nighttime. The left image shows the room rendered under natural light. The right image shows when I render it with a real world spectrum, and in the evening, we can see the same room, how it looks like during the day and in the evening. Yeah, here's another example. If I use electrical light, I can pick up different color spectrums compared to the left one. The right one can give us more yellowish tone. Okay, next, not just for living space, we also focus on kitchen remodeling, which is more challenging because kitchen has a lot of intricate objects. Here, we detect the kitchen area and refurnish it with a new set of kitchen components. And the same set of kitchen components, we change the layout. And then we can select a new set of kitchen components. For example, different cabinet color, different background wall, and different countertop materials. So we can combine furniture layout plus kitchen remodeling, and then get a new indoor panorama using this approach. And then now the question is, I didn't change the view position here. For indoor lighting analysis, not just for photorealistic rendering, we also care about the absolute illuminance map. The RGB image maybe looks decent, but if we convert it into illuminance map, it's a different story. Here, the left image shows a virtual rendered scene cropped from panorama, and the right image shows indoor task lighting. For example, if I want to do reading, the target illuminance is 300 lux on the task surface. So I set up 300 lux as a benchmark. We can see some areas are underlit, some areas are overlit. And because we have a 360-degree panorama, so we can visualize this space from different angles. And we can compute the average illuminance value from the desk surface, which is outlined in yellow color here. Okay, specifically, if we sitting in front of the desk, we can select 3 different desk materials. The first one is glass, second one is marble, we can see it's very shiny. The last one is a wooden cover, so we can see less shiny effect here. So first we can choose to slightly move the desk closer to the couch. However, most of the areas are underlit if we look at the desk area. And then we can choose to rotate a little bit, looking at the window. In the meantime, we can add a desk lamp at the top of the desk, and then we can see some red area on the desk surfaces, meaning the light level is increased. And then once we add a ceiling light, we can see a lot of red pixel here because the light level is pretty high here. So we have some ongoing work about estimating indoor heat map. Right now we saw the light transport. We have a light source, scene geometry, and the reflectance, how it looks like from the visible light. And then since we have all those components, we have a light source, we have the scene geometry, we aim to solve heat transport. Because heat has 3 different ways: convection, conduction, and radiation. And we hope to get another panorama which can tell us the temperature of the room. Okay, in summary, this study we have achieved to use paired indoor and outdoor images for virtual home staging. And the whole process only takes several minutes. We send the image in and get a new image out. We can do a lot of different design alternatives and iterations here. Yeah, in the meantime, I captured the HDR data set on my own. And we can see 137 plus 141 in total, like 278-ish paired indoor-outdoor images. Each scene is annotated with room orientation, luminance value, and illuminance value. And I manage the data set, and it's open to public. So please let me know if you want to download it. Yeah, and if you want more information, you can visit our project website. And this work is funded by Zero Group. Yeah, thank you.
Have you taken the obvious step of going to VR?
Not yet, but I think user study is very important. So we can do 2 different user studies. One, ask a housing agent to run my code, run the pipeline. Also, another user study is, like you said, put the image into VR headset. Yeah, that's a very good question. Yes, that's a good question. So we use deep learning approach to estimate the 3D geometry here. From here to here, we have solid 3D model, but it's not from manual modeling. It's from the deep learning model. Yeah, but to be honest, it can only give us a shoebox model, which is a planar surfaces. It cannot give us too many details, like a window frame or like a ceiling. Because here I have another example. This room actually has double layered ceiling. We cannot model that because it's all simplified as a flat plane. So that's a little bit limitation for this work. Yes.
Geometry.
What?
You didn't touch the geometry.
Yeah. 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 So this is the input, and in the middle is our system. We send an image in and get a new image. Yeah, we didn't use any commercial software. Only data collection is manual. Data collection is manual. Yeah. Let me go to electrical light here. Yes. Oh, we have solid furniture object. And then we have the light spectrum. We have a light model. Yes. Yeah. Yeah, yeah. Because for rendering, we need a geometry and a material. Sorry, Greg.
Capture and shoebox model. Well, looping those, building the pattern.
Yes, yes.
Is that an AI?
So for semantic segmentation, there are a lot of models, and we select the most recent segmentation model and use that into our pipeline. And then because the furniture layout, for sure, just like right now, we need to know the geometry. Then we can place the bed and the couch. Yeah. Oh, good question. Yeah, good question. So here, the input is floor mesh and furniture objects. We know the floor boundary. Here I use, we know the window, where the window is. And we also will find the floor edge to guide the layout. We need the information from the floor geometry to guide the furniture layout. Yep. Yes. Yep. Oh, it's an image imprinting model named Lama, L-A-M-A, image imprinting. Just like, because Photoshop can do this thing, but Photoshop is manual. Lama model, as long as we can send the original image plus the binary mask, it can imprint the furniture object. Yeah. Yes, yes. Yeah. Oh, good point. So the layout estimation will give us the actual dimension, and it can give us the height of the tripod. And all the unit here is in meter. Yeah, so we don't need a measurement. Yeah. Yes. Good question. So I use some furniture data set. For example, Adobe has a data set and also that different furniture data set.
3D.
Yeah, 3D. So furniture has geometry material. We only need those. And then we can incorporate that into rendering model. Yeah. So you can select your preferred furniture from the data set. Like IKEA has a virtual furniture data set as well. Yeah. 3D. Yeah, it has to be 3D.